there, my name is Christopher Worst and welcome to the first video for the Transport 1. This is the first video in the Homework 1 playlist, going over part 1, that says, given the velocity profile in the angular direction in the gap between concentric cylinders, where k is the ratio of inner to outer radii, then it's given us the angular direction equation. The angular velocity is equal to w multiplied by that ratio of inner and outer radii squared, so k squared, divided by 1 minus k squared, all multiplied by big R being the outer radius squared, divided by some inner radius r minus, again, that same inner radius r, where w is the angular frequency in radians per second as a function of radial position r, show that the torque on the inner and outer cylindrical surfaces are equal. It also gives us the shear rate in cylindrical coordinates as sigma equals the radius multiplied by the derivative with respect to r of the angular velocity divided by said radius. So I'm going to swap over to the camera only so I can work this out on the whiteboard behind me. So I'm going to draw out a picture. Start over on this side. We have a outer cylinder, and an inner cylinder, and the inner cylinder's height is h. Now I'll also draw a top-down view because that will be important later. So in there, the inner radius is Ri. It's not a good angle. It's better. The outer radius shown is R, and that arrow is the angular velocity. So I'm going to copy down the angular velocity equation as well as the shear rate in cylindrical coordinates as given by the homework problem. And again, I have the homework problem here on my computer. So the angular velocity is equal to omega, that's that w, it's omega, multiplied by k squared, k is the ratio of inner to outer radii, k squared divided by 1 minus k squared multiplied by r squared divided by r, where big R is the outer radius and little r is some inner radius, again minus that inner radius. I'm also going to write down sigma, where sigma is the shear rate in the cylindrical coordinates, is equal to some inner radius multiplied by the partial derivative of that angular momentum divided by some inner radius. So, with this, we know that k, I'm going to do it over here so we have all of our equations up top. We know that k is equal to the ratio of inner to outer radii, so Ri we'll call it, Ri being inner radius, and big R. We also know that torque, what we're looking for, I'm going to call it, use big capital T as it. It could be tau, but we've also got tau as a different as a shear rate in a different form, so we're just going to use capital T. So torque is equal to force times radius. And then here we're going to use tau for shear stress, not in the cylindrical coordinates, is equal to force applied over area. So now we're going to take this velocity, this angular velocity here, and plug it in to this shear rate equation, but we're going to do it step by step. So, angular velocity divided by radius will be simply nothing changes with this first two bits, the omega and then k squared divided by 1 minus k squared. And we're just going to divide this bit by r. That makes it outer radius squared divided by inner radius, or some inner radius squared minus, since that's r over r, just 1. Now we're going to take the partial derivative with respect to r. Since r squared is on the bottom, we treat it as r to the power of negative 2. And since everything else is not little r, the inner radius, it's treated as a constant. So that means that the derivative is the same as this, except this 1 is gone. It's a derivative of a constant. And then negative 2, because the derivative of anything to the power n is n multiply n, that thing, we'll call it x, to the power of n minus 1. So r is to the power of negative 2, it's negative 2r to the power of negative 3, r to the power of negative 3 goes to the bottom as r cubed. We've got our derivative, and let's finish up by multiplying it by r. And to do that, I'm just going to add it here because I don't want to have to crouch or run out of room down here. R, the only thing that changes is this r cubed. That's not good. Goes to an r squared. Now, we've done this, we've done this. Now what and why does it matter? Take this and make it for sigma of two different, the two radius, the inner radius and the outer radius. So let's draw a little wall here to cordon it off. And we'll say sigma of r equals ri. Sigma for the shear rate for the inner radius in the cylindrical coordinates is equal to, plug this in with ri substituted for r, negative 2 omega k squared. I'm just combining different parts of the formula. 1 minus k squared multiplied by r squared over ri squared. We also have, and since k is equal to ri times r divided by r, we know that ri, I'll draw an arrow down, ri is equal to k times r. So that means that is equal to negative 2 omega k squared, 1 minus k squared, r squared over k squared r squared. Now we can cancel some things out. R cancels, k cancels, and it's equal to negative 2 omega over 1 minus k squared. And that is specifically for this inner radius. Now let's do the outer radius. So sigma r is equal to big R, capital R, is equal to negative 2 omega k squared, 1 minus k squared, r squared over r squared. These two cancel out. We're left with negative, that's 3. Negative 2 omega k squared over 1 minus k squared. So, we have these two. I'll box them in for you. Easier to see. We have these two, which we're going to be using later. Now, let's set up a torque formula to get all of this wrapped up together. One last thing we're going to need is that this shear stress is also equal to mu multiplied by sigma. Okay, see where we're going with this. We're going to end up taking this sigma and plugging it in. But we have all of this. We have torque. Let's start writing up. I'm going to make another recording off a bit. Start writing up a torque equation for the different radii. For R equals Ri equals force multiplied by Ri. Now, we have this equation here where the shear stress is equal to force divided by area. That also means that force is multiplied by the shear stress times area, or is equal to the shear stress times area. Goes to torque at the inner radius is equal to shear stress at the inner radius, R equals Ri, multiplied by A. We have that multiplied by Ri. This torque we're going to plug in to be mu sigma. So that goes to torque at the inner radius is equal to mu sigma A Ri. And because we're going to need we're going to need to make A its own function. A is equal to the area of a cylinder, 2 pi RH. So in this case, A will be Ri. In the next case where R is equal to the outer radius, capital R, it will be capital R. So that means I'm going to start plugging things in for sigma. We know that if it is Ri, it is mu negative 2 omega over 1 minus k squared multiplied by 2 pi Ri squared h, because this Ri and the Ri in the area combine. So we have that. We have the torque for the inner radius. Now I'm going to go underneath down here, which means I'm going to have to squat to do the torque for the outer radius. So torque for the outer radius is again equal to force times outer radius is equal to shear stress of the outer radius multiplied by A multiplied by outer radius. You can then plug that in. To make it mu sigma AR, A capital R. And again, we're going to plug in this time from the sigma for the outer radius, for the shear radius, the cylindrical coordinate for the outer radius. So I'm going to write that below it, make another line. Torque for the outer radius is equal to mu -2 omega k squared over 1 minus k squared multiplied by, we know, 2 pi r squared h. Now, to finish things off, I'll write it over. I'm going to take it and write it over here by our pictures. We want to prove that the two torques are equivalent. So torque at the inner radius is equal to torque at the outer radius. Goes to mu -2 omega over 1 minus k squared 2 pi ri squared h equals, I'm running out of room here, so I'm going to cordon this off. I'm just going to put it below it. Equals mu -2 omega k squared over 1 minus k squared multiplied by 2 pi r squared h. Now, because there are some things in both equations, we can cancel them. So, for example, mu cancels, -2w cancels, -2 omega cancels, 1 minus k squared as a whole cancels, 2 pi cancels, and h cancels. That gives us, and I'll write it down here, that gives us ri squared is equal to k squared r squared, and because everything is squared, we can simply get rid of it. That gives us ri is equal to k r, and since we have this up top, down here is the same as up here, we know that this is true, and therefore, in a roundabout, literally we went around the board, apologies, ran out of room. We've proved that the torque at the inner radius of two concentric cylinders, the torque at the radius of the inner cylinder is the same as the torque at the radius of the outer cylinder. Now, thank you very much for watching, and I hope you have a wonderful day.